Good morning, students. On Monday, we were discussing about Module 3, Distributed Database Concepts. So in the previous class, we discussed the topic So we were discussing about types of distributed systems. So they are heterogeneous, homogeneous. In multi-database. All the sites, nodes will have the same backend and front end. Say in our distributed database, we have 5 nodes, 5 sites. The site 1, 2, 3, 4, and 5 all are with the same configuration, front end and back end. In case of heterogeneous, the site 1 is of hierarchical database, site 2 of relational type, site 3 of network, site 4 is of object oriented, and site 5 of object oriented type. So it means that they are using different back end, and the front end is also Unix, Linux, Windows, Macintosh, like that. They are using different front end and different back end systems. So any doubt with the and how we can represent all 4 types of distributed databases means? From the diagram, you can easily understand. Say if you take the all 3 parameters, that is autonomy, distribution, and so if you take x-axis as autonomy, so if you take the traditional centralized database system, it takes the value of in the x-axis autonomy is of more than 50 points, and y-axis distribution is only 0 points. So x is 50, y is 0, and z-axis also 0. So in traditional centralized database systems, the autonomy will be very high, but the distribution and other parameter will be very low. If you take the second type, the point mentioned as the pure distributed database systems, the distribution will be very high. Here it takes the y-axis value as more than 50, and x-axis is 0, 50, and the z-axis is 0. So based on the autonomy distribution and other parameters, we are categorizing the distributed databases as purely distributed database system, traditional distributed database system, and federated database system, and multi-database or peer-to-peer distributed system. Trying to connect through the laptop, it's taking time. Hybrid systems, federated systems, and multi-database systems. So we have four types of distributed. One is homogeneous, second is heterogeneous. In heterogeneous, we have federated and multi-database, and in hybrid systems, we have a federated database system as well as multi-database. So any doubt so far? So the next topic is federated database management system issues. So if you go for different types of distributed database configurations, especially in case of federated database management system, what kind of issues we will face? So we will say the point C, where we'll have x-axis autonomy as 0. That is, autonomy will come into minus 10, and y-axis is again minus y, minus 10, and z-axis alone we will have some points of 10. So that kind of database is called federated database system. So in federated database systems, what kind of issues we will face means difference in data models, because in federated systems, the data models schema used in different sites will be of different type. Say variety of data models like a relational database management system, object-oriented database management system, hierarchical database management system, and networked different types of database management systems will be used in case of federated type. In that case, to deal with uniformity via the single global schema or process them in single language is challenging. So in different sites, they will use different database languages. Say the headquarters, they may use MySQL. In the regional office, they may use SQL. In another place, they will use OQL because they are using object-oriented database. In another place, they may use normal Sybase or DBase. So like the different languages, backend is used. So applying the common schema among all the sites is very difficult. And if you want to share the data from one site to another site, we need to convert, or we need to change the content to process the, say if you are receiving an object oriented Neo4j or MongoDB database from the headquarters, if it is sent to a hierarchical database where they are using SQL or they are using Sybase, so processing an MongoDB database in SQL is difficult. But if you send an SQL table to the MongoDB, it will process. So the higher end query processing systems will process the lower end processing. But if you are receiving object oriented databases to one normal SQL hierarchical or relational database model, it cannot able to process. We need to do so many conversions. So difference in constraints. Each site may have their own data accessing and processing constraints. So the constraints what we are applying in OQL cannot be processed by SQL. And the constraints which we are applying in hierarchical database like Sybase or DBase, that cannot be processed by the higher end models. Differences in query language. Some site may use SQL, some may use SQL 89, some may use SQL 92, and so on. So if they are using different varieties or different hierarchical models and processing in a common centralized database is very difficult. So these are the main issues we may face if you are going for federated database management system where the backend is of different types. The next thing is semantic heterogeneity. So as we discussed, semantic means so any doubts so far? The types of distributed database management systems like homogeneous, heterogeneous, federated, and multi-database. And what are the issues we are facing in federated database management system? Any doubt? Okay, all of you mention your attendance in the chat box. Okay, Atish Gowda, Shrikar. So I will mark down. So if I'm not missed out your name, then only you will say attendance. Atish, Shrikar, Sai Vaibhav, Banu Prakash.
Present, ma'am.
Yeah, Manideep, Ashok, Devika Menon.
Manideep present, ma'am.
Yes, Halini, Arshit.
Yeah, Banu Prakash present, ma'am.
Yeah, I'm reading out as per the participants. I am marking in the paper. If your name is missed out, then you tell me lost. Arshita Gupta, Jayasuriya, Sai Prasad, Mrudul, Chandrapol, Prakash, Shivam Gupta, Shreyas, Anil Sai, Arshit, Preetham, Mani Manasa, Aki, Arvind Gowda, Shail, Radhika, Santosh Kumar, Jayant, Olivia, Sadhvi, Santosh Raj, Amina Begum, Santosh Kumar S, Vijayan. Okay, our next topic is semantic heterogeneity. So it occurs when there are differences in the meaning, interpretation, and intended use of same or related data. So if you are using different databases in the backend, and if you are trying to share the data through common network, and if it is maintained in the centralized database, so that time, if you are using different databases in the backend in different sites, there will be definitely an issue in sharing, updating, modifying, and creating the schema, giving access rights, all those things. Create the biggest hurdle in designing global schemas of heterogeneous database. So if you are using heterogeneous, different configurations in terms of a database, software, operating system, software development, other embedded softwares, definitely there will be issues in maintaining the common schema or global schema, and maintaining the common design templates is an tedious task. Design, in case of design autonomy, it refers to their freedom of choosing the following design parameters. We already discussed what is autonomy. Autonomy means they can work as a standalone unit. They can take any decision. They can use their own schema. They can use their own design templates. They have the freedom to use different front end and processing layers as well as the back end. So they will be given freedom, or they will be given the rights to do design their own models, schema, and other optimization techniques. The universe of discourse from which the data is drawn. So representation and naming. So if you are how we are representing this replica fragments, vertical and horizontal fragments, all those things will have the naming schemes, and creating the replica and creating the other reports that will the representation and naming of data elements and the structure of the data model may be pre-specified for each local database. So they each and every site will have its own schema, will have its own naming. So they may use different names, different for each sublogical units or fragments. The understanding meaning and subjective interpretation of data. This is chief contributor to semantic hierarchy. So maintaining their subjective interpretation of data. So based on the fragments, based on the reports, what they are generating, they usually, if the data is shared among different sites, a common naming system, a common templates, keywords will be used to represent each fragment and each logical unit of the data. But if you are using different heterogeneous backend, in that case, maintaining common templates, maintaining common and naming space, naming system, and common method isn't, that will create confusion among different people. So that is also an issue. So the transaction policy constraints, so that this deals with serializability criteria, compensating transaction and other transaction policies. So how we are how to deal with the serializability criteria and compensating transactions. So the transactions performed in each and every local site will have its own templates and other transaction policies. We cannot apply the common transaction policy among all the sites if you are using heterogeneous backend system. The next important issue is derivation of summaries. So creating aggregation, creating summarization of common reports, annual reports, and other data processing features and operations supported by the system. We cannot go for common design or common reporting format or common schema. So these are the major issues we may face if you are using heterogeneity in the backend. The semantic heterogeneity will create issues in following common design autonomy, following from which the data is drawn, and representation and naming system can be common. Understanding and meaning of interpretation of data will be different for each site, and policy and its constraints cannot be applied common. And derivation of summaries, creating the summarized reports, creating the annual reports, following a common template, creating aggregation and summarization. So those things will create an following those things in common is an tedious process. Communication autonomy, ability to decide whether to communicate with other components in the distributed system. The communication execution autonomy, say the ability to execute local operations without interferences from external operations by other component, and its ability to decide the order in which they execute. We cannot go with common things in case of execution autonomy also. Say the waiting for, say the sites will be doing the transaction, and the centralized core server will commit the process. That will also in that can also cannot be given, because each site is following its own schema design as well as the backend tool, front end and backend tool. So the internally it should be done. The association autonomy of your component, ability to decide whether how much to share its functionality and the resources with other components. So if they are using heterogeneous backend, in that case they cannot share the resources cannot be shared. The server site 5 is using object oriented database, and site 2 is using hierarchical database like SQL, or they are using Sybase or DBase. Sharing the resources, the configuration is here, sharing the resources like printer or server or memory, or utilizing the CPU power, or utilizing the local server database. All those things is not possible if you are going for federated and heterogeneous database schema. And distributed database architectures, we may use parallel versus a distributed. If you take parallel or versus distributed architectures, two main types of multiprocessor system architectures. So we can go for, in the distributed environment, we can go for parallel processing, as well as we can go for multiprocessing also. So if you are using shared memory, tightly coupled, shared memory means the memory of one site can be used by other sites, and tightly coupled means the memory, the server, say the nodes are having their own memory or server. In that case, that is tightly associated with the schema and the logic design of the particular site alone. It's totally dependent on the particular shared memory. In that case, multiple processors share secondary storage and also share primary memory. In that case, the same processor can be shared by more than one site, as well as the data will be available in the particular site server as well as in the main server also, and the local disk will have its own data. And shared disk loosely coupled architecture means multiple processes share secondary storage, but each has their own primary memory. So if you take, from the diagram you can easily understand. Say the first diagram shows you some different database system architectures. It's a shared nothing architecture. The diagram A shows you shared nothing architecture. In that case, the site 1, computer system 1, computer system 2, and computer system yet. The computer system one is its CPU, memory as well as database. So the memory is database is belongs to the system one alone. In that case, the content of system one database is not accessible to other sites. If they want some data, only the fragments or the replica will be generated based on the request, and that alone will be shared. The local server of each system is not available to other systems in the distributed environment. So the databases are tightly coupled with the systems. If you take the second type, a networked architecture with a centralized database at one of the sites. So in the diagram B, we have n number of sites, and all are connected through the communication network. And the centralized site will have each site is not having any server, or they are not having any personalized high-end CPU. Only the local memory will be available in site 1, which is located in San Francisco, site 2 in Network, New York, site 3 in Atlanta, site 4 in Los Angeles. And the centralized server is available in the headquarters, Chicago. The database is completely maintained by the centralized server, main headquarters. Each site, they are not having any centralized, they are not having any server. They have only the local CPU to do the transactions. Only the hard disk will be there. There is no separate server for each site, like San Francisco, New York, Atlanta, and Los Angeles. Only the headquarters central site, Chicago, is having database 1 as well as database 2, which is maintaining the complete database of all the distributed systems. So this kind of network, this kind of architecture is called centralized database at one of the sites. Here the headquarters. To take the diagram 3, we can see a truly distributed database architecture where we have all 5 sites. Each site is having its own database, and the content of all the sites is accessible to all other sites. So any site 5 can access all the remaining 4 sites database without any restriction. The same way site 4 also can access site 5, 1, 2, and 3 databases without any restriction, because it's truly distributed. Any site can access any site, all having there is no client or there is master slave. In case of the diagram B, you will call it as master slave. The headquarters central site Chicago is called master server or the main server or core server. The remaining branches are only the sites with the local CPU. So these are the 3 major types of distributed database architectures. First one is shared nothing architecture. Second one is networked architecture with a centralized database at one of the sites. The third one is a truly distributed database architecture. So any doubt with the 3 types of distributed architectures? Any doubt? So we have shared memory, tightly coupled, and loosely coupled means the remaining sites can access, and tightly coupled the server attached to the site is alone accessible. And if you take the shared nothing architecture, there won't be any sharing, but all are in the network. If they want some data, then they can place the request through the proper channel or through the headquarters. And if it is approved by the headquarters, then only the data from one site will be, that to not all the data, only the requested data alone will be available to, will be shared with the other sites. So in a shared nothing architecture, every processor has its own primary and secondary memory. No common memory exit. So each node is having its own primary memory, RAM, as well as the secondary memory, maybe the magnetic disk, or it may be the secondary storage devices or backup systems. And the processes communicate over the high-speed internet network, has symmetry and homogeneity of nodes. So all will follow the same configuration, but only if a necessary comes, then only the data will be shared through proper channel. So we have parallel versus distributed systems. In that, we have a shared memory, tightly coupled architecture, shared disk, loosely coupled architecture, and shared nothing architecture. To take the general architectures of pure distributed databases, the global conceptual schema, CGS, global conceptual schema, CGS, which provides network transparency. So in that case, a global schema, if you are having 10 sites, all the 10 sites will follow the same global schema. The same schema. Say the schema means what? We will have the number of, we will represent the schema in terms of entity relationship diagram. In the entity relationship diagram, you can see if there is a table called employee, all the attributes related with the employee table will be mentioned. And if there is one more table called projects, how the project table and the employee table are associated, whether it is one-to-one, one-to-many, how many, say in the employee table, there will be a number of projects. So there are the relationship between employee and projects table is one-to-many. And in the same project, there will be a number of employees. So it is many-to-many. The same way, departments. A employee may belongs to only one particular department. So we can have a number of tables like employee table, project table, department table, and regional office, branch office tables. Like that, we have a number of tables. How the tables are interconnected and how they are, what is their access rights, whether it's one way or two way, or is there any primary key, secondary key, reference keys among the tables. All those things will be represented by using entity relationship diagram. You can say that is a complete schema. So the common schema will be applied to all the number of sites in the distributed environment. So in case of general architecture of purely distributed means each and every site is available to all other sites. There is no restriction. All are having the equal rights. And in that case, we will use the global conceptual schema, CGS, which provides network transparency. So there is no hidden, there is no any hidden concepts. All are having equal rights. All can share the data. Everything is visible to all other sites. Each node is having its own local internal schema. So depending upon the region or depending upon the site, it will have its own policies, government norms. So they will have the local internal schema also based on physical organization details at the particular site. Say if there are so many VIPs in a particular region, or if there are more particular business transactions in a particular region. So according to that, a specific local internal schema will be followed. Logical organization of data at each site is specified by local conceptual schema. So based on the location, based on whether it is in headquarters or in a particular city or in a urban village. So in that case, based on the constraints followed in the particular region, local internal conceptual schema will be followed. The CGS, that is global conceptual schema, LCS, local conceptual schema, and their underlying mapping provides the fragmentation and replication transparency. So based on the CGS and the LCS only, how we are transferring, how we are creating the fragments, vertical fragment and horizontal fragments, and how the replication, how the replicas are shared with other sites, and what is the transparency, whether it is completely they can read only, write only, or update, modify, what are the rights given. So all those things are fixed based on CGS and LCS. Global query optimizer refer to both global and local conceptual schemas and generates optimized local queries from global queries. So how we will optimize them? Because while processing any query in the distributed environment, we are using the query optimizers. So in the query optimization process, we have 4 stages. The given schema or query will be converted into corresponding algebraic expression. Then the optimizer converts and processes the algebraic schema by using the best optimal method. Then it will be converted to the fragments will be generated. Then the 3 steps are followed by CGS. The 4th step is followed by the LCS. So in the distributed environment, we'll have the query optimization process. The query optimizing algorithm will be chosen based on the local conceptual schema. Say the schema which is followed in New York cannot be followed in Kanakapura. Say, but the branch, the same bank may be available in Kanakapura as well as in New York. So if you are they are having some branch in headquarters, New York, and they are having one more branch in Yedavanalli or in Kanakapura. So the schemes, the number of the customers and the type of processing, the corporate, there will be more corporates in the Bangalore headquarters, but less corporates in the Kanakapura region. Only farmers and village people will be there. So like that, based on the type of transactions happening in a particular branch, the LCS will be fixed. Cost function and estimate cost based on response time. So the cost which we are spending for the various transactions like CPU time, input output processing time, network latencies, how much time we take to process, and so we are placing a query and it takes 5 minutes to process the query and to generate the report. So the speed may be less in a particular region, and in some other region the speed will be network speed will be very high. Some places they may be using 4G, some other places they may be using 5G, 2G. So the latencies, delay in the transaction, all those things are estimated. Estimate the size of intermediate results. So those things are based on the CPU time, input output processing time, network issues and latencies, network delays. All those things are based on the local conceptual schema. So these are the general architectural issues which we may face during pure distributed systems. So we need to remember what is global conceptual schema, what is local internal schema, and what is the role of CGS, and what is the role of LCS, and how the CGS and LCS is fixed, and what are the conceptual schemas, and how the optimization of data query processing is maintained in different sites, and how much time we are spending to, how much CPU time, processor time, and input output processing time, the cost, time, and the latencies, memory access, as well as the network issues and other, everything will be measured in terms of time and cost. And if you take the optimizer, selects the candidate with the minimum cost of execution. So what is the role of a query optimizer means? It will choose the best optimal method. Some places it may choose um, it will choose the algorithm and methods based on the location. So whether the particular site will support for the particular algorithm or not, or whether the network is available or not, how much time it will take for the central CPU time and the server time, how much time it will take for the input output, everything will be calculated through the query optimizer. According to that, it will choose the best optimal method. Each local DBMS would have its own local query optimizer. So the local query optimizer will be available in the LCS itself, transaction manager and execution engineers, as well as the local system catalog, which houses the local schema. So in LCS itself, we'll have the query optimizer, transaction manager, execution engines. So all those things are depending on the local optimizer. The global transaction manager is responsible for coordinating the execution across multiple sites in conjunction with the local transaction manager at those sites. So what is the role of CGS means? It will show you the best method, but that method is not supported by the particular site. Then it will go for the best other alternative methods. Say it is trying to process through OQL, but the site is the only hierarchical database. It will not support object-oriented databases. In that case, the local query optimizer will choose the best optimal method to process the query based on the configuration. So these are the things we need to consider while using different types of heterogeneous configurations in case of distributed environment. So as we discussed, we have three major types of distributed architectures: shared nothing architecture, and a network architecture with a centralized database at one of the sites, and the third one, a truly distributed architecture. So any doubts so far? From this diagram, you can easily understand the schema architecture of distributed databases. So how the schema is chosen and how the schema is executing in case of distributed database means, say we have two users, user 1 and user 2. User 1 is accessing the external, the user is accessing the database through the external view. In this case, we can take it as the ATM system. So a customer who is having the ATM card, debit card or credit card, he is going to the ATM system. He is inserting the his debit card in the ATM to do some transaction. So he is accessible to only the external view. External view means only he can see the screen. He don't know what's happening in the server, what's happening in the database. Then when he interact with the system through the debit card, the global conceptual schema CGS will check its card, because I may have the card from Bangalore. Bangalore branch office. I may do the transaction anywhere. I can do the transaction in Pune or I can do the transaction in Calcutta. So in that case, the CGS, Global Optimizer Schema, will identify the particular person is a customer or not, where the card is issued, whether the account is with the Pune office or it's in the Bangalore office. Then it will identify whether the card particular bank or, and if it is whether it is enabled or it is having access rights in all other sites or not. Then check whether the account holder belongs to the parent office or the branch offices. Then all those things will be checked by the global conceptual schema, because it's a conceptual schema for the entire system. Then it will according to the, say if I am using a Maharashtra Bank, then it will check with the Maharashtra Bank databases. Say if I am using this ATM machine of SBI, but my card belongs to Maharashtra Bank. Then if it is Visa enabled, I can do the transaction in any ATM machines. Then it will, after identifying my account belongs to Maharashtra Bank, it will transfer the, it will go to the local query optimizer of Maharashtra Bank database. Then again it will go to the local internal schema, because my card belongs to Bangalore office, Bangalore branch. Then it will access the table from the particular region. So local internal schema of Bangalore will be enabled, because my complete data will be available in the particular subtable. Then it will go to the directly stored data. So it will have the access rights to the particular table where my account details are available. And that account details, the data where it is stored means it may be stored in the site 1. In the same branch itself, there will be a number of, say in the Bangalore city itself, there will be a number of branches. Say in the Bangalore itself, we may have 20 or 30 Maharashtra Bank branches. So within that, which branch my account belongs to, whether it belongs to Majestic or it belongs to some other, say Shivaji Nagar or KR Market. So it will go to the particular branch where my account is completely operated. So in that way, so we have this superset, the subset called CGS, with the subset called LCS, with the local schema LIS. So in that way, it will segregate. It will come in deep to the. So we are going like a divide conquer. So the complete system, then we are dividing it through the LCS. Then again the LCS is into a number of LIS. Then within the LIS, we will have a number of sites. It will go to the particular site. So in that way, the schema architecture of distributed database system is doing the processing. So here the access rights and the privileges and other internal autonomy and other design rights will be based on CGS, LIS, LOS and LIS, as well as the stored data. So based on that, for federated database architecture, we know very well the autonomicity will be very high, but distribution and parameter is very case, and it will be using different configuration in the backend. One will be using a hierarchical, another will be using networked, another one will be using a relational database, another one may be using object query language, object oriented. So in the case, how to local schema component database, and the component schema is derived by translating the local schema into canonical data model or common data model called CDM for the FDS. So in federated database management system, the global schema will be different and the LCS will be different, LIS will be different. So if each one is having different languages and query processing techniques, then we will go for common data model. So the different models will be converted into the common data model or canonical data model through the CDM mapping of one model to another model so that it suits. So we are using adapters. We are using different, if it is not supporting, we are going for adapters. So through the adapters, we can convert one type of data into another type. So by using the common data model, the processing will be done. The schema translation from local schema to the component schema is accomplished by generating mappings to transform commands on the component schema into commands of the corresponding local schema. So we will use the translation, schema translation. One type of schema is converted into another type of schema by using the common data model techniques, and after converting so that it can compact with the destination node, the processing will be done. The export schema represents the subset of the component schema that is available for the federated database systems. So we'll have the export schema. That the export schema will represent that will convert the higher end models to lower end models, as well as it will convert so that it can operate on the particular destination node through the subset of components that is available in any whatever federated database we are using. There it will be available. The conversion process is available. The federated schema is the global schema or the view, which is the result of integrating all the shareable export schema. So it will federate the data into another model by using the global schema view, which is the result of integrating. So we'll integrate different models to another model so that it can be processed. The external schemas define the schema for the user group or the application as the 3-level schema architecture. So it will convert one type of schema to another type of schema through the 3-level schema architecture. So from the diagram, you can easily understand the 5-level schema architecture in the federated database system. So it is the 5 layer, or we can say 5 level. The first level, we have external schema. The second level, we have federated schema. Third level, we have export schema. Fourth level, we have component schema. And the fifth level, we have local schema, where it can be, the local schema will be understandable to the component DBS. Say if somebody cannot able to understand some language, so then we will have the translator. And the translator knows only one language, he don't know the language, what we will use one more interpreter. So like that, in the federated architecture, we are using different CGS, LCS, and LIS. So we are in need of we will use some layers of architecture so that one type of schema can be converted to another type of schema, and that can be converted to another type of schema which can be understandable to the LIS. So we have 3 layers: CGS, LCS, and LIS. So in between, there is no compactability. What we will do, we will use so many other internal and external schemas so that CGS can be converted to another type of LCS. Again, the LCS can be converted to another type of LIS. Again, the LIS will be converted to so that it can understand the local schema. Say, any doubt with the 5 level schema architecture? So this is called 5-level schema architecture of federated database system. So this federated database system, what is federated means? The backend that will be different. So in a distributed environment, all the backend should be in the same query processing model, because we are dealing with the tables. All the tables should use this common CGS, LCS, and LIS. If they are using different backend, say SQL, MySQL, and OQL, and MongoDB, Neo4j, Sybase, Oracle, DB2, like that. If they are using different backend, they will be having their own global conceptual schema, their own local conceptual schema, their own local internal interpretation process. So in that case, to convert one type of schema to another type of schema, so that they can share the data as well as they can share the information among themselves. So we are going for conversion, and that can be accomplished through the five level schema architecture of federated database system. Any doubt in this topic? And we have one more topic called a 3-tier client server architecture. So here 3-tier in the sense we have 3 layers. So in the previous federated architecture we used 5 layers, but we have 3 CGS, LCS and LIS. In between CGS and LIS we have 1 layer. Again LIS to LCS to LIS we have 1 more layer. So we had totally 5 layers. And if you go for 3-tier client server architecture, there will be an so there will be tuition exam. So more than 1,000 students are paying the fee. There are 1,000 clients, and the server is all are linked to SVA Connect. So this one server, all the people are accessing the site to do some transaction. So clients will go for 3 layers of processing. The following 3 layers, the first layer, the server through some website or through some node, that is called client node. We call it as presentation layer. Say we will username and password or mobile number, USN number and some data. So that is called presentation layer. The server is presenting to the client through some layer where they can interact through the application programmer's interface. We will interact with the system. The second layer is called application layer, where the actual processing, say if you are crediting something, the credit process will be accepted, it will be validated, the actual amount will be transferred from your account to the bank account or to the college account. Here in your account, the debit will be done. In the college account, the credit will be done, and the receipt will be generated. So that is called application layer, where the actual processing, addition, subtraction is happening. And the last layer is called database server. Once the processing is over, the data will be updated and committed. Committed means it will be saved permanently in the main memory as well as in the server. So that is called database server. So where we are accessing, say in the ATM system also, we are accessing the ATM machine screen, that is front end, or we will say the client side or presentation layer, and the actual processing is done in the CPU available in the ATM machine itself. That is the processing layer. And once the processing is over, the data will be updated through the network or through the internet. Database in the backend server, that is called database server. So in any client server architecture, 3 layers. So the presentation layer provides the user interface and interact with the user. Through the user interface only, we are interacting with the system. So it plays a platform for client to the server. The programs at this layer present a web interface or forms to client in order to interface with the application. So it will provide the web interface so that you will have so many buttons, user-friendly commands. You can easily understand, enter your name, enter your PIN, and choose the transaction. We want the receipt, like some interactive messages, user-friendly messages will be available to interact with the system. Web browsers are often utilized, and the languages are specifications used, like we may use HTML pages or XML pages, or we may use extended HTML hypertext markup language scripts, or we may use CSS common separated files or Flash Flash or MathML or scalable vector graphics, SVG components, or we may use Java pages or JavaScript pages or Adobe Flex pages. So any user-friendly, any API, application programmers interface front-end tool will be used to design the presentation layer. And this layer handles user input, output, and navigation by accepting user commands and displaying the needed information. So it will give you some, it will display some welcome message, then it will ask you to enter the password, then it will validate the password, then it will say what transaction you want to change the mobile number, or you want to do the credit or debit, and it will give you some user-friendly messages. When a web interface is used, this layer typically communicates with the application layer via the hypertext transfer protocol. So whatever information we are entering in the screen, that will be transferred to the middle layer, processing layer, through the hypertext HTTP protocol, hypertext transfer protocol, because most of the front end and back end, everything is interconnected through the HTTP protocol, through the internet or through the web pages. And how it performs means we'll have the client. So on the client side, we have user interface or presentation tier or layer, where we will use a web browser or HTML pages or JavaScript or Visual Basic kind of front-end tools. Then it is connected to the application layer through the HTTP hypertext transfer protocol. And the data will be transferred from client to the application server. In the application server, we will use the business logic or processing actual transaction, actual calculations will be done in the application server. And here we for the transaction and calculation and programming purpose, we will use Java programs or C programs or C++ or C# or application programs. And once the processing is done, actual calculations, the transactions are performed, then the data will be transferred back to the database server through ODBC or Java JDBC or SQL or CLI or SQLi. So object database connectivity, through the connectivity, the application layer content, the transactions will be updated in the database server. In the database server, we'll have usually the server is updated through the query and transaction processing tier. Here we will use the query processing languages like database access, SQL, PSN or XML, DB2 or Oracle commands. Or we may use mangoDB or Neo4j or OQL commands. So these are the three layers of processing happening in client server architecture. Client server architecture itself is an distributed database architecture. Any doubt in this particular diagram? So we will end with this topic. And if you take the application layer, it is called business logic. Actual processing, actual transaction processing is done here. So this layer programs the application logic. Example queries can be formulated based on user input from the client. So whatever input we are you giving, that will be processed. Or query results can be formatted and sent to the client for the presentation. So whatever query we are placing, that will be processed and sent. It will be sent to the front end also. Additional application functionality can be handled at this layer, such as a security check, identity verification, and other functions. So checking, validating the password, checking username and other data, and accepting the inputs, doing some transaction that happens in the application or business logic. The application layer can interact with one or more databases or data sources as needed by connecting to the database using ODBC, SQL, or other database access techniques. So whatever transaction calculations we are performing, that should be stored in the table or file. So that will be sent to the backend tables. And in the database server, what it's doing now, this layer handles query and updates requests from the application layer, processes the requests and sends the results. So whatever query we are placing, credit or debit, that option, if you are choosing a credit button, so the credit query will be enabled. Say add that that will be enabled, and that whatever the data we are entering, say credit, I am crediting 5,000, that 5,000 will be accepted as input, that through the query that will be sent to the server to update in the backend table. And the query results may be formatted into XML when the transmitted between the application server and the database server. Say if I am entering crediting 5,000, after 5,000 is added in my balance, again it will send an acknowledgement to the application layer. Say 5,000 is added. Now the balance is 50,000. Previously it was 45,000. Now it is 50,000. So now it will show balance. My balance is 50,000 from backend to the application layer, from application layer to the front end. So like that, the data updation, actual data will be processed and saved in the database server. So any doubts so far? So today we discussed what are the 5 layers of federated database management system, and how the client server architecture is doing the process by using 3 layers: front end, middle layer, and back end. So these are the 2 major topics discussed today. So you go through the topics. I already uploaded PPT in the Google Classroom. You go through it. If you have any doubt, ask me in the next class. You have any class? Friday you have any class? Sorry, Saturday you have any classes? If you are free, we will schedule 1 class on Saturday. The class representatives A session and B session. If you want, if you are free on Saturday, we can schedule some class from 10 to 11 or 11 to 12 or 1 to 2. You message me, we will have 1 more class. All of you answered your attendance. So you go through the topics. If you have any doubt, ask me in the next class. Amina Begum entered your attendance. Manideep. So if you entered your attendance, you can leave the class. Halini, Jayasurya, Mridul. Yes, if you entered now, you can exit. Nitish, Preetham entered. Vijay, Mani Manasa entered. Santosh Kumar, Jayant entered. Shadvi, Santosh also entered. Santosh Kumar, yes. Have you entered your attendance?
Yes, ma'am. Just now.
Yeah. Nitish, Vijay, and Mridul. Okay, those who entered your attendance can leave the class. Okay, I will end the class. Thank you all.